Oh, yeah. Thank you for the invitation. Thank you for the introduction. It's a pleasure to be in Paris always. So, yeah, as I understood, this was announced as a seminar in geometric representation theory. So I decided on some subject which has both some representation theory, some geometry, algebraic geometry then. And, well, so my home turf is really the representation theory, and the algebraic geometry is kind of second language. So there are some parts of which where I don't know all the details. Okay, yeah, so today I want to speak about the Kazhdan-Lusztig conjecture, and well, I do it in the context that I know of representations of reductive P-Adic groups. So I will say something about what this conjecture says in this case of P-Adic groups, and well, how you can approach it, and what the current status is, and also at the end what you can do with it. So let's focus first on some standard representations of reductive groups, and well, these will be over non-Archimedean local fields. And well, what is such a standard representation? It's a representation which occurs in the setup which was originally devised by Langlands, as far as I know. So you start with a parabolic subgroup, and of the Levy factor m of this parabolic subgroup, you take an irreducible tempered representation, and then you take parabolic induction to G. That's one way to get a standard representation, but that's not all of it. You must be more general. You can also say, okay, I take this tempered representation of this Levy subgroup M, and then I tensor this up with a character of M which is unramified, but not only that, it in fact has positive values, and it's positive in the direction of your parabolic P in a suitable sense. And then you tensor your tempered representation tau with this character chi, and then you take this normalized parabolic induction, and that's by definition a standard representation in the context of reductive P-Adic groups. And well, the name probably comes from this main result about standard representations, that they are built or are a very important step in the classification of all irreducible representations. Namely, it can be shown that every such standard representation has a unique irreducible quotient representation. And moreover, if you take two standard representations, then they produce the same irreducible quotient if and only if the data that you put into it were equal. Well, not only equal, but in fact that if the data are conjugate by your entire group G, then they produce the same irreducible representations, and otherwise they do not. And in fact, in this way, one can obtain every irreducible representation of a reductive P-Adic group exactly once if you take into account this equivalence of standard representations. So that's very good, and Langlands did this originally in the context of real reductive groups, but it holds just as well for reductive P-Adic groups, and in fact it holds also more generally for certain algebras which involve a root system. That's somehow the main point, that it boils down to statements about root systems. Okay. And well, okay, so one of the first things you may ask about these representations, are they sneakily irreducible themselves? Because then this quotient business wouldn't be necessary. And well, in fact, it turns out that, yeah, almost always they are irreducible. So if you write down a bunch of examples, then most of the time you will find that they are irreducible, but they are not all the time irreducible. And well, certainly for the purposes of this talk, the most interesting of these standard representations will be the ones which are reducible. And then, well, okay, people have asked various questions about this reducibility of standard representations, and well, one of these questions or conjectures was called the standard module conjecture, and this applied then in a well, more specific situation where the group was a quasi-split reductive group, and the representation, the tempered representation from which you started was a generic representation, and then it was conjectured quite so long time ago by Kasselman and Shahidi that this standard representation obtained from these data is irreducible if and only if the Langlands quotient that you build from it is generic. In that case, the Langlands quotient coincides with the full standard representation, but apparently this is only possible if well, yeah, that's the only possibility if you require that this Langlands quotient is generic. And this has been shown mainly by Volker Heiermann in collaboration with other people. So this is one of the interesting questions about it. But okay, you may also ask more generally, if this standard representation is reducible, what can you say about the irreducible quotients? Well, so this also goes back quite a while. So this is what the Kazhdan-Lusztig conjecture says something about. It provides some expression of what the irreducible subquotients of a standard representation are in terms of geometric statements about which involve Langlands parameters and nilpotent orbits and local systems, perverse sheaves, all defined in terms of this complex algebraic geometry, which one can build from Langlands parameters, which are associated to P-Adic groups. The precise statement I will come up with later. It requires some preparation to actually say precisely what it does. But yeah, this is very nice, and this, originally Kazhdan-Lusztig, they didn't work with P-Adic groups at that time. I think they first looked at like complex semi-simple Lie algebras, where you have the original version of the Kazhdan-Lusztig conjecture saying something about Fermat modules and irreducible modules for semi-simple complex Lie algebras. And there they had this Kazhdan-Lusztig conjecture post somewhere second half of the 70s, I think, which was also proven, by now a long time ago. And then they didn't really formulate the analogous conjecture for P-Adic groups, as far as I know. It may have been around at the time, but it was formulated, to the best of my knowledge, only by David Wogan in a 1993 paper. So, okay, let's look at some examples of standard modules which are reducible. So the first such example is obtained, from GL2 or from SL2 if you prefer. And you take as tempered representation, the trivial representation, and then the positive character by which you twist the thing. You have to choose it precisely if you want to have reducibility, and one way to choose it precisely is to take the square root of the norm character and the inverse of the square root of the norm character. And if you do that, you get a representation which actually has length 2, and in this case it has the trivial representation as a quotient and the Steinberg representation of GL2 as a sub-representation. And one typical thing that one can see here already is that, the sub-representation has various nice properties. This is a tempered representation. It's in fact a discrete series representation of GL2, and it's also a generic representation. And the quotient representation, the trivial representation, doesn't have any of these properties. So in general, for these standard modules, the sub-representations tend to have better properties than the quotient representations. Well, in this case, it's length 2, so there's just one quotient, just one sub-representation, and there are no other things to talk about. If you want to look at the standard module which has length larger than 2, okay, you have to look a bit further. There's no one for rank 1, I think, but for rank 2, root systems, this is possible, and you can do this in the group GL3, and then you can take as tempered representation, the Levy subgroup is again the maximal torus. As tempered representation, you can again take the trivial representation, and one character to achieve this with is to say to take the norm character tensored with the one character on the middle position of your torus and the inverse of the norm character on the third position of your torus in GL3. And if you parabolically induce this character, then, you get in fact a standard representation of length 4. And, similar to like for GL2, it has the trivial representation as a quotient, and it has the Steinberg representation of GL3 as a sub-representation. But now there are two other things which are sitting in the middle, and those are obtained from intermediate Levy subgroups, so subgroups of GL3 which are isomorphic to GL2 times GL1. And up to conjugacy, there are in fact 2 such subgroups. And for both of these subgroups, what you can do is you take on the level of the Levy subgroup, you take the Steinberg representation tensored with some character, and you take the parabolic induction of that, and then you get, another thing, which is a standard module for coming from an intermediate Levy subgroup. You divide out the Steinberg representation, which sits in there, and then you get a thing which occurs as an irreducible subquotient of this particular standard representation. So already in this example, it takes some effort to analyze precisely which four things occur in here. Here I can still write it down precisely, but okay, if you go to further things, it becomes quite difficult to do this by hand. Okay, now let me try to say something about how to formulate the Kazhdan-Lusztig conjecture precisely. So, okay, in this case we have to involve the Langlands parameters of this representation. So, first we have to assume that we know how to associate to one of the representations we're interested in some Langlands parameter, otherwise you cannot say what we're going to do. So, okay, we take the Langlands duo group as usual, and in this case, in this setup for Langlands parameters, the most convenient formulation is you put them in the W-de-linie form. So you take a homomorphism from the W group to the Langlands duo group, and on top of this homomorphism you take one nilpotent operator, and this nilpotent operator, well, it's here called n, and the next line it suddenly has become x, but okay, the n lives in this variety of all possible x's. So the action of this, well, the image of the W group should conjugate this nilpotent operator, and this conjugation operator should multiply it by eigenvalues, which will be powers of QF in some sense. So here we see that already you have some kind, you have we have a complex variety there, this thing called G phi check. So the fracture G is the Lie algebra of the complex duo group of G, and the subscript phi means that, well, okay, that we restrict to this subset, which consists only of nilpotent matrices. So this is in fact a variety of nilpotent matrices, and well, okay, it's in fact a vector space here. So it's a very simple-minded thing as a variety. But if you look at the action of, say, the group, well, the centralizer of phi in G on it, then it becomes interesting. So, this is what I already said. Yeah, okay, the centralizer in G check of phi, it acts on this vector space. And, well, now then you can translate the data which you get from a Langlands parameter plus an enhancement of this Langlands parameter into a more geometric fashion. So an enhancement here would be an irreducible representation of a suitable finite group, which occurs as the component group of the centralizer of this entire Langlands parameter. But in this case, you can also say, well, okay, this is now a representation of a finite group, and it's associated to one nilpotent element of this vector space, and then from this representation on one point of this nilpotent vector space, you build a local system on an orbit for this group which acts on a vector space, because well, the local systems on one orbit for a group acting on something are in bijection with the irreducible representations of the equivariant fundamental group associated to one point of this orbit. So in this way you can build from this Langlands parameter geometric data, namely an orbit of nilpotent elements, plus on that orbit an equivariant local system. And well, so then that's just what I said. Okay, you can then reformulate what you consider as Langlands parameters as some homomorphism from the W group to the Langlands duo group, plus on top of that a local system on a suitable nilpotent orbit in the Lie algebra of your complex dual group. And this is the formulation of Langlands parameters, which is convenient to phrase the Kazhdan-Lusztig conjecture. So, okay, and the Kazhdan-Lusztig conjecture, well, what will it say? It will tell you, given a standard representation, how often does every irreducible representation occur in this standard representation as a subquotient. So counted with multiplicities. And well, you need, given one standard representation which comes from a certain Langlands parameter, you don't need to look at all other irreducible representations. You need only look at other irreducible representations for which the first part of the Langlands datum is the same. So they have the same Langlands parameter phi, but maybe a different nilpotent element n, and maybe also a different enhancement of this parameter. And then from that you need to cook some multiplicity, and well, then there's really where you do something geometric from this. Well, from these two things, these two enhanced language parameters, you build, well, two local systems on nilpotent varieties, and both you promote to intersection cohomology complexes. So those will be perverse sheaves living on not this one orbit, but on the closure of an orbit. So it will still, they live on some subset of this vector space G phi check. And then you have two things to compare. Well, you have one intersection cohomology complex, whose support is the union of a certain number of orbits for this the centralizer in G check of phi. On the other hand, you can compare it with some other local system, and then you can you can make sense of some multiplicity. But of course, already this multiplicity, well, you need to be a bit, you need to think a bit about what does it mean exactly. So I say, okay, I built this intersection cohomology complex, and then I via this operation I star, this just means pull back to the nilpotent orbit where the other Langlands parameter lives. But okay, you can do that, but this intersection cohomology complex is by definition something which lives in the derived category of sheaf. So yeah, to make this precise, actually you first have to pass to cohomology to make sense of this multiplicity, and this is not included in the notation here. And so, okay, I'm not sure I need this, but okay. We know we need to assume that there is a reasonable form of the local Langlands correspondence, and this reasonability includes that the part phi of the local Langlands parameter will classify more or less what the cuspidal support is. So in this sense, this standard module business says you only have to look at standard modules and irreducible representations which have the same cuspidal support, and this is what kind of explains why you need only have parameters with the same phi. So now I can finally phrase this Kazhdan-Lusztig conjecture, namely if you have a standard module, which I called here E, phi, and rho, so it comes from the local Langlands correspondence, but it would be a version of the local Langlands correspondence which translates Langlands parameters to standard modules. And on the other hand, well, I have a second object here, an irreducible module M, phi, n prime, rho prime, so this really comes from the local Langlands correspondence as people know it, and then you may ask what is the multiplicity with which this irreducible module appears in this standard module, and Kazhdan and Lusztig say, okay, it's the multiplicity which you can express in these geometric terms as here above, namely you take this intersection cohomology complex of the one Langlands parameter, you put it back to the orbit where the other Langlands parameter lives, and then you take the multiplicity with which this local system appears in this intersection cohomology complex. But for some reason, which at this point is very unclear, you have to exchange the orders. So somehow, we will see later that this comes out for some geometric reasons. Okay, so yes. Yes.
But then it's not perverse any longer.
So no, indeed.
So there is a sign for it.
Well, this is a bit how you set it up. So indeed, the thing is here. Yeah, I really have to take the cohomology sheaf, and then I just add the multiplicities in all possible degrees, so to say. But I do not do this with a sign. No, remarkably enough, it's not. So this, and yeah, in principle, you would say, okay, it's in a derived category, so maybe you should take some kind of Euler characteristic thing, and it would be more natural to take an alternating sum. But yeah, that would be true, but it's not what happens on the side of the representations. So in fact, if you look at how Vogel formulates it, he does have such an alternating sum. But in fact, if you, well, later we will see in terms of representations that this naturally is not the case there. So let's check it in this one case where we had this standard module of length 4. In that case, we can make everything rather explicit. So this was for GL3, where you have this one unramified character of the maximal torus of GL3. And, well, okay, here the Langley's classification has been known for ages, or the Langley's correspondence. And you can just write down the Langley's parameters because it's know how to do it on this torus, and then you have to add some nilpotent elements to it. But okay, here let's not add nilpotent elements immediately. Let's analyze which nilpotent elements are possible given this character of the torus. So you have to check this, well, this eigenvalue condition and the possible nilpotent elements from a two-dimensional vector space, which I wrote down there with coordinates, say, A and B. And then it's not so hard to see that in this two-dimensional vector space, there are actually 4 orbits for the action of the diagonal torus, depending on whether or not the one of A and B is 0. And, well, okay, then you can match the orbits with the possible, well, 4 representations in the L packet here, or not in the L packet, but that occur in the standard module. And you have a largest open orbit, which corresponds to the Steinberg representation. You have a smallest orbit, which is just the 0 nilpotent element, which corresponds to the, well, yeah, to the trivial representation, or the trivial representation irreducible as quotient, but this standard module, I think, and you have 2 things in the middle, which correspond to other things there. And, well, if you look at this list, you will see that in this standard module of length 4, all 4 possible irreducibles appear with multiplicity 1. And on the other hand, you can also look what happens there geometrically. Well, in this case, the geometry is rather innocent because all varieties here inside are smooth and non-singular. So all these intersection cohomology complexes will again be local systems on the appropriate varieties, and all the multiplicities between these local systems and intersection cohomology complexes will just be 1. So, okay, this is a simple-minded case, but at least it works here, and all the multiplicities are 1, which is probably rather typical for GLN, but only for GLN. So, okay, now I want to say a few words about how I approach this problem in terms of well, Hecke algebras. And, well, there are various aspects which I will just sketch, because it would take a long time to really explain very well what's going on. So the first thing to observe is that this is it's a second-order conjecture. You already need to know a local Langlands correspondence to write down this Kazhdan-Lusztig conjecture. So you must decide how you want to approach such a second-order conjecture in the first place. And if you don't want to intend to first prove the entire local Langlands correspondence, because that would be too hard. So there are several approaches. Well, one thing is say, okay, I do it only in cases where I already know the local Langlands correspondence. Well, that's very good. You can do it for classical groups or things like that. And this, yeah, I think some of these cases have indeed also been done in the past, certainly GON, but maybe also classical groups. I'm not entirely sure. You can also say, okay, maybe I don't want to restrict to all those cases, but I just do it and I assume that there is a local Langlands correspondence and it works in the way which I want, and then I prove what I can for this Kazhdan-Lusztig conjecture. Also, this has been done. Well, I did it slightly differently. I thought, okay, I would rather not do it depending on some things which I've not shown now for sure. I first try to prove some statements purely about representations of P-Adic groups, and then in such a way that if I can combine it with the Langlands correspondence, then it will prove me this Kazhdan-Lusztig conjecture. So this is in some sense reducing one second-order conjecture to 2, well, first-order conjectures. And I'm not going to prove the local Langlands correspondence, but I am going to prove the other part. Okay. Yeah, you need to get some geometry into play, starting from these representations of reductive P-Adic groups. And well, traditionally one of the methods to analyze representations of P-Adic groups has been by means of Hecke algebras. And this, well, of course, everybody has seen the famous statements about the Ivory spherical representations, where you can look at a certain class of representations of a reductive P-Adic group and then transform this into an equivalent class of representations of certain affine Hecke algebra by means of taking vectors which are fixed by the Över-Horry vector, Horry subgroup. And well, this has been a field of investigations for a long time. But by now it is understood that you can play a similar game for every reductive group and every Bernstein block in such a reductive P-Adic group, and you can at least build something like an affine Hecke algebra, not entirely that, but close to it, which describes, well, the module category, or whose module category is equivalent to one Bernstein block in a reductive P-Adic group. So this you can say this corresponds to describing all representations of a reductive P-Adic group where you start with all cuspidal supports which are given by a ramified twist of one particular supercuspidal representation sigma von Levy subgroup, and then allowing all possible operations that you can do to build new representations. So this is possible, but it's slightly messy because you cannot, at least at the moment, we cannot really control exactly that we get an affine Hecke algebra. So it turns out it's better to restrict to a somewhat smaller class of representations where you say, okay, I restrict the possible cuspidal supports. I start now with one supercuspidal sigma of a Levy subgroup M, and I tensor only with unramified characters which are positive. They take positive values. It's a smaller class of representations. It still has representations of infinite length. They need not be completely reducible. You can do many things still, but it's a smaller class of representation. Things have become a bit easier, and then you can describe it with a somewhat easier algebra called the graded Hecke algebra. And well, this way to analyze representation of P-Adic groups works better in a sense. You can do it always for every reductive P-Adic group, every supercuspidal support, and you get always an algebra of a particular form. So that's good. It's still not complex geometry, but that comes then in the next step, which is certainly less well known. But it turns out that if you have such a graded Hecke algebra and it has nice properties in the sense that its parameters are of a certain kind, then in fact you can rewrite this graded Hecke algebra as the endomorphism algebra of a certain perverse sheaf, or maybe a certain direct sum of perverse sheaves. So that's a tricky thing to do, and it's not, it really is it's a translation step from P-Adic things to, complex algebraic things. It doesn't work always because there is a condition on certain parameters which you need to find from your representations of P-Adic groups. So, so let me say also a bit about that. So just to say what is the status of this. So in general, this is what I mentioned before, but in general you need to, if you want to get some complex geometry into play, you need to find at some point in your play a graded Hecke algebra with nice parameters, and Lusztig has in fact conjectured not all too long ago that this is it always works well. Whatever your reductive P-Adic groups you start with, whatever cuspidal support you start with, the graded Hecke algebra that you construct from it will always have parameters which you can also find in some way from complex algebraic geometry involving nilpotent orbits and local systems. And Lusztig did this motivated by his own investigations of unipotent representations. I've tried to check this conjecture in many cases, and the conjecture reduces to the case of simple groups. That's not too hard. And for simple groups, in fact, most simple groups you can deal with. Not all of them, but okay, most of them you can deal with. And the others are probably true as well, but we do not know how to show it currently. So the upshot is, okay, this way to analyze representations of reductive groups via reduction to Hecke algebras and then reduction to some geometric setting is probably going to work in almost all cases, and we know for sure it works in a large majority of cases. So that's good. So now let me say a bit more about how we really get this complex algebraic geometry into play. And this goes into the nature of what is a graded Hecke algebra, or one of the ways to get a graded Hecke algebra. So well, the first way in which these algebras were obtained was just by something in terms of generators and relations. And only later it was realized that you can also get them from a certain complex algebraic setting, namely, well, you take a reductive group, you take a Levy subgroup, and on this Levy subgroup you take a nilpotent orbit, or in the Levy or in the Lie algebra of that, you take a cuspidal local system of that, and that turns out to be sufficient data to produce an algebra. And this algebra is then, well, okay, first you need to produce a certain thing called here K, which is a direct sum of perverse sheaves, and it will be living on the Lie algebra of G, where there will be an action of this group G, or well, I call it G tilde, but okay, G, and there's also an action of a group C cross just by scalar multiplication, or maybe the square of scalar multiplication. And then you take some kind of endomorphism algebra in the appropriate category. So that's, well, yeah, it involves a lot of technique for sure. I have myself spent a lot of time to get to terms with what the heck does this say. So first of all, already the definition of this object K from which one takes the endomorphisms is rather complicated. And from Lustig's papers it was a mess. But later on I understood what goes on. It's in fact, it's a, well, say an algebraic geometry analog of parabolic induction for reductive P-Adic groups. So the data give you a local system on a nilpotent orbit. Nilpotent orbit is here called OV, so it contains an element V. Well, you extend this in a trivial way by, well, taking the direct sum of this OV with some vector space, the center of your Levy L, and the unipotent radical of this Levy subalgebra P, or parabolic subalgebra P, and then, well, then you have a local system on this part which is still equivariant for the Levy subgroup L, but you can make it equivariant for the parabolic subgroup P just by saying that the unipotent radical of the parabolic acts as trivially as possible. And then you can lift it to a G equivariant local system on this part, where the subscript P tilde means that you have an action of P on both of these factors, and you have divided out by this, by the combination of these actions. And, well, then you have a local system there on the right-hand side, and then finally you push it back to G, where you have a natural map from this space to the Lie algebra G just by, well, multiplying the things in the sense that you let the group G act on the other part by the adjoint action. Then you go back to the Lie algebra G, and you push forward your equivariant local system to G. Well, you have to make sure you push it forward in the right way. It's here the push forward with compact supports. And of course, everything takes place in these derived categories, so that makes it also a bit more difficult to understand exactly what it does. But okay, the essence is you have started with some cuspidal object associated to a Levy subgroup of your complex reductive group G, and via some version of parabolic induction, one has constructed from this a certain, well, semi-simple complex of constructible, equivariant constructible sheaves, which lives then on something associated to your group G. And this is then the object from which one may consider the endomorphism algebra. So, okay, let me say more precisely what you can really prove about this. And what you can prove about this in representation theoretic terms concerns a rather small category of representations, namely representations where you say there's only one possible cuspidal support. I mean, these representations, you may stack many of them onto the top of each other, you may stack sums, you make extensions, and so on. So it can still, there's still infinitely many things to play with, but it will be a category where you have only finitely many irreducible objects. And, well, okay, under some mild assumptions about these parameters of Hecke algebras, which are going to be true in any case, you can say, you can prove, in fact, that okay, if coming from just these data of G and this supercuspidal of a Levy subgroup of G, you can construct a graded Hecke algebra, and you can see that this graded Hecke algebra can be obtained in some geometric way from, well, data from complex algebraic groups. And well, then moreover, you can say this omega, well, yeah, it defines you in principle a Bernstein block, and in this Bernstein block we restrict to one cuspidal support, and this corresponds on this graded Hecke algebra also to restricting to, well, say, representations which have one fixed central character, or maybe extensions of representations which have the same central character. And in that case, you can translate this category of representations of G with only finitely many objects to a category, well, the module category of this endomorphism algebra of, well, again, another equivariant constructible sheaf considered in a suitable derived category. So that's, yeah. That's also a nice statement which really translates representations of P-Adic groups to something which is expressed entirely in terms of complex algebraic geometry. And there's again another mysterious object K sigma, which depends not only on the previous K, but there's also involved now some semi-simple parameter which lives in the Lie algebra of your complex algebraic group. And this is constructed more or less in the same way as the K which we did before. We apply this kind of parabolic induction procedure until at this point here we have an G equivariant local system, and then we do not push it forward immediately to G, but first we restrict it to a smaller subset which is associated to this sigma, and only then we push it forward to the part of G which is associated to this sigma. So yeah, this is variation on previous thing. But again, this well, yeah, complex of sheaves K sigma is obtained from the data that you put into it, a cuspidal local system and some semi-simple parameter via some version of parabolic induction. This is how I like to view it. And well, I have spent quite some time on trying to make this equivalence of categories better, say, okay, the endomorphism algebra of some perverse sheaf or direct sum of perverse sheaf, can you really write this down in terms of it is some category of sheaves or something like that, but well, it turns out this is problematic. Somehow, yeah, the module, just as an abstract algebra, it has more modules than you would see in geometric terms, the modules which you can obtain from testing against certain perverse sheaves. So this is the best formulation that I have come up with so far. On the other hand, there are conjectures of Vargas-Schulze which say something similar, but these conjectures are, well, they're slightly different in the sense that they don't involve constructible sheaves, but rather coherent sheaves, and apparently this difference is well, responsible for the fact that here it doesn't work, and in the Vargas-Schulze setup it supposedly works. Okay, so now let me say something about how to approach this Kazhdan-Lusztig conjecture in this context of these Hecke algebras, graded Hecke algebras, which are obtained from complex algebraic groups. So first then, one needs to construct the objects, the standard modules and the irreducible modules in these geometric terms so that they will correspond via this previous slide to the standard modules and the irreducible modules from a P-Adic group. And well, okay, let's see. Well, okay, I noticed that in fact there was a subtle difference between all the endomorphisms of this perverse sheaf K and the ones which I wanted for my P-Adic group, because somehow in this purely geometric formulation there was this action of C cross by means of, well, a scalar lambda will act by lambda to the multiplication by lambda to the power minus 2, and this is essential in this setup, but somehow in your P-Adic group side you don't see this back, and if you manipulate it well enough you can get rid of it. And then you, well, this means that somehow in this algebra you must specialize a certain form of variable to a certain real number, when this is the appropriate real number, and then here you replace equivariance for this entire group G times C cross by equivariance. Well, you forget about the factor C cross and you look only at the stabilizer of the semi-simple parameter. So this is a kind of technical thing to make it more workable. And then from that setup, well, the standard modules can be constructed rather directly. So you have some kind of set perversive sigma. You can push it back or pull it back to one point, and then you take the cohomology, and this turns out to be a module over your algebra that you're interested with. Unfortunately, again, you have to be careful which kind of pullback you take. Here you must take the exceptional pullback. It's something which you really can do only for well, on the level of the derived category, otherwise you may run into trouble. And well, so that's almost a standard module, and then you must involve some irreducible representation of a finite component group to produce from that actually a standard module which has a unique irreducible quotient. And from this context, it's not clear, but one can prove that this really corresponds to the standard modules from reductive P-Adic groups. And well, another part of the same story says that indeed this is a standard module in the sense that if you do this construction and it doesn't produce you the zero module, then it has a unique irreducible quotient. And in fact, yeah, well, all irreducible modules of these graded Hecke algebras that you want to look at are obtained in this way via this construction, and again somehow from parameters which are unique up to conjugation. And in fact, well, if you do some work, you can write down an expression for this irreducible quotient in the sense that it's somehow this intersection cohomology complex is just one of the direct summands of this K sigma, and this K sigma is exactly the direct sum of various things of this kind. Okay, and yeah, well, so as I said, like for P-Adic groups, for these graded Hecke algebras, you have a similar situation that, well, yeah, you have the standard modules, you have the irreducible quotients, and this gives you bijection between standard modules and irreducible modules, and the standard modules can be parameterized by geometric data consisting here of, well, semi-simple element sigma, a nilpotent element y, which has a certain commutation relation with sigma, forcing it to live in a certain vector space, and an irreducible representation rho of a suitable component group for these data semi-simple element and nilpotent element. So this is all pretty similar to what people have observed in the local Langlands program, namely what would happen for Langlands parameter. Only so far, the advantage of this setup is that I have not used anything from local Langlands correspondence. This is all just built from starting from Bernstein components of reductive P-Adic groups and translating it via various Hecke algebras until you get something geometric, and they are analyzing graded Hecke algebras and proving these things. So it looks almost the same as for local Langlands correspondence, but it is really not that. It's entirely about reductive P-Adic groups. Okay, but now, well, okay, in this setting you can say this provides you a geometric way to construct representations of reductive P-Adic groups, because here you have a standard module and irreducible module, and you can translate back via some 5 translation steps to get representations of your reductive P-Adic groups if you want to do so. Well, probably usually if you do that, you don't have much information left in the end because the translation steps are rather complicated after each other. But it does provide you some way to parameterize irreducible representations and standard representations. That's also something. So now, okay, now let's try to compute the multiplicities here. So this has already been done by Lusztig so some time ago. In this purely geometric setup, now we have some formula for what is a standard module in terms of, well, prefer sheaf, pull back to a point, take cohomology, and then maybe also involve an irreducible representation rho. And you want to semi-simplify it and then compute multiplicities. And well, okay, if you just say, okay, let's already assume it's semi-simplified, then you can write the whole thing down, or you can express the whole thing, because this whole sheaf K sigma is a direct sum of intersection cohomology complexes which are indexed by this direct sum. You can express the whole thing like this, and then on the right-hand side you have something which was identified as an irreducible module, and on the left-hand side of the tensor product there you have a multiplicity space. And so that's expressed here in this second line. And then I have also sneakily change this one kind of pullback to another kind of pullback, which is allowed by some results of Lusztig. So there, then one gets there some way to express, well, yeah. Well, you just get a semi-simplification of your standard module. It's standing there. You just have to replace the left-hand side by the dimension of this space to really compute the multiplicities. And this is what Lusztig already observed in some paper. Well, you have to look very hard in this paper to see that this is what it says. But this is that's the point how to formulate it, that this result of Lusztig actually shows you that the multiplicity with which a certain irreducible module appears in a certain standard module, both constructed in this wave of Hecke algebras and complex algebraic groups, is equal to some geometric multiplicity of, well, one local system in, well, one intersection cohomology complex, and then take the cohomology of this complex and only then compute multiplicities. Hey, what happens there? Sorry. So this maybe answers your earlier question about do we need to take some alternating sums in computing these multiplicities. Well, no, this earlier result of Lusztig tells us we don't, because you have to, actually everything is evaluated by pulling it back to one point, and there you replace this intersection cohomology just, well, by the cohomology of the pullback to one point, and then you don't have to deal with the alternating sums anymore. So this is the main reason, the main geometric reason I feel why this whole Kazhdan-Lusztig conjecture for reductive P-Adic groups will be true. At this moment, this is a theorem about, well, graded Hecke algebras, but, well, with our previous comparison of representations of P-Adic groups and representations of graded Hecke algebras, we can now transfer this to P-Adic groups. So suppose we are in a reasonably good situation where this can be done. You can compare representations in a certain block for reductive P-Adic group with representations of a certain geometric graded Hecke algebra. In that case, now the previous results about representations of geometric graded Hecke algebras produce you a result about the representation of the P-Adic group, which is a version of the Kazhdan-Lusztig conjecture. It's not exactly the Kazhdan-Lusztig conjecture because I haven't used the local Langlands parameters anywhere. So I cannot say I've proven this because I haven't even used the Langlands parameters. But it's very similar because you've seen it always. It involves complex reductive groups. It involves things which look like Langlands parameters to some extent. But so what I did is I have translated the Kazhdan-Lusztig conjecture to a statement about geometric graded Hecke algebras, which is also a complex algebraic geometry, and I've proven that statement, which was fine with me, because I already knew that in most cases from this statement I could prove it for well, in the way Kazhdan and Lusztig designed it. If you know that there is a local Langlands correspondence which has reasonable properties, then this version of the Kazhdan-Lusztig conjecture can be promoted to the real version of what was conjectured by Kazhdan-Lusztig and Vogel. So, well, I'm going to say that now, I think. So suppose, well, okay, suppose you have some Langlands parameters. And suppose there is a local Langlands correspondence, well, not just abstractly, you need to know something, so which I summarized here by saying this Langlands correspondence must be constructed in some way via Hecke algebras. This is not a very precise statement, but it does hold in many cases. And in those cases, well, one can in fact, well, you can promote these results to P-Adic groups and Langlands Kazhdan-Lusztig conjecture also involving local Langlands parameters. And here's a list of cases for which this local Langlands correspondence is known, well, with sufficiently many nice properties. But in fact, this list is supposedly not exhaustive because I believe it's always going to be work for every reductive P-Adic group and every Bernstein component there. But okay, these are the cases where so far it is definitely known. So you can also say this provides an alternative proof of the Kazhdan-Lusztig conjecture, certainly for GON, but also, I guess, for some classical groups for which it had been done before. Or some representations of certain classical groups, I'm not entirely sure. So this is yeah, this is the current state of the art about the Kazhdan-Lusztig conjecture. It's known for a reasonable class of groups, and the method is probably going to apply to other groups as well, but at the moment this is hard to prove. Progress there will be slow, but it will be forthcoming at some point. So, in the last part, let me also say something about what can you do with it. Or, well, first what I did with it, and then what other things. So you can also, well, relate it to the question of what are the sub-representations of a standard module. Not only the sub-quotients, but the sub-representations. And I recall there was this standard module of Kasselman and Shahidi, which said something about this in the case of generic representations. But, okay, you can also look at it more generally. So suppose we have this Kazhdan-Lusztig conjecture. We know something about multiplicity of an irreducible module in a standard module. And then, well, it turns out that this multiplicity is in fact, well, it's in some sense entirely obtained by homomorphisms from the irreducible, well, not from the irreducible module, but from one standard module to another standard module. So if I want to compute how often a certain module m, y prime, sigma, rho prime appears in a standard module E for y, sigma, and rho, this is in fact, every time it appears is accounted for exactly by a one-dimensional space of homomorphisms from the associated standard module to the same standard module y, sigma, rho. And this is, well, I don't know, it just followed from the geometric situation. It wasn't predicted before as far as I understood, but the Kazhdan-Lusztig conjecture, well, gave you one of the, well, one half of it, say one estimate, and then the other estimate is really that you must be able to produce a sufficient amount of homomorphisms of representations between two standard modules. And if you know how these standard modules are constructed in terms of geometry, in terms of local systems, and you look very carefully at that, you study this in detail, and from that you can actually explicitly write down a bunch of homomorphisms which do the trick. So here, this is really the part where the most geometry are involved. And among other, this tells us that if you have two standard modules, then you can never map one standard module to a standard module where you have a nilpotent parameter which is larger, but you can always map a standard module to another standard module where the nilpotent parameter is smaller. Well, okay, there's a condition on the rho and the rho prime, but okay. So maybe that's not always, but in any case you can say it like this. A standard module will not map to another standard module where the nilpotent parameter is in a larger orbit. And so this is going to tell you something about properties of standard modules and their quotients. So let's check again what it does in this earlier example of this standard module of length 4, which came from GL3. We had, well, fixed one character of the torus, say norm times 1 times norm inverse, and we had a bunch of the nilpotent vector space of nilpotent elements parameterized by two complex numbers A and B. And, oh, not so fast, we had from this 4 standard modules and 4 irreducible modules, and the most interesting thing was this standard module here, pi b t triv chi, which had in fact length 4 and contained all the irreducible modules with multiplicity 1. But you also have these other standard modules. Well, you can fit them all into this picture, where you can see how what you can map. So on the bottom line, you have the smallest nilpotent orbit, which corresponds to the largest standard module, and all the other standard modules which have the same Langlands parameter, but maybe not the same nilpotent element of this Langlands parameter, you can map to there in a natural way. And in fact, the space of module homomorphisms is one-dimensional for each of these arrows, so there's not too much choice. And well, you see in here that you can map from the largest possible orbit, which corresponds to the smallest possible standard module. You can map to either of the other two in the middle, and you can also map to the one down directly, but I didn't write down the arrow there. But there are no maps in this diagram which go up, or just only the 0 maps, but that doesn't really count. So this is somehow the geometric situation, how you can compare standard modules for, well, where the parameters have the same semi-simple part of the parameter, but different nilpotent parts of the parameter. And well, one other thing to observe here is that if you look at the top of this diagram, where you have the largest possible nilpotent orbit, there the standard module is in fact an irreducible module. It's a Steinberg representation. And in the other three cases, the standard module is in fact reducible. And this is also a typical behavior, namely if you have Langlands parameters where the nilpotent orbit is as large as possible, then the associated standard module is irreducible. So this is, well, at least initially I proved this for Hecke algebras, so for these graded Hecke algebras, because there one can analyze it. So you may consider, well, parameters where you have a nilpotent element y prime or y and a semi-simple element sigma, and suppose that now this y prime is as large as possible in the sense that the orbit of this y prime is an open subset of this vector space of nilpotent elements that came into consideration in the first place. Well, in that case, well, then you have this comparison of standard modules and then you can see nothing else, no other standard or irreducible module will map to your module parameterized by y prime and sigma, and as a consequence, this module, standard module from y prime and sigma and rho prime must be irreducible. So the upshot here, standard modules obtained from parameters which have nilpotent elements in the open orbit tend to be irreducible, at least for these Hecke algebras. Well, you can promote this result by checking, okay, suppose you have one standard module, inside there you have another standard module, and this other standard module comes from a parameter which has an open nilpotent part, then in fact the same considerations tell you that the number of times the one thing occurs in the other is in fact already accounted for by homomorphisms from one standard module to the other, and as a consequence the irreducible module from an open parameter, if it appears in another standard module, it can only appear as a submodule, and you can only appear by coming from a concrete map from one standard module to another standard module. It will never appear as a quotient of a standard module. So that's another funny thing which you get here as, well, properties of modules whose parameters are open. And, well, again, this is only for Hecke algebras, but it also works for Langlands parameters. Only there, I cannot prove it in this many cases, but the strategy is the same. So this is a notion which came up a few years ago, the notion of an open Langlands parameter, which just means that, okay, you take your Langlands parameter in very linear form, then the phi specifies a certain vector space consisting of nilpotent elements. The n must be chosen from this vector space. Well, it has been known since Kazhdan-Lusztig that the centralizer of phi acts on this vector space G phi check with only finitely many orbits, and in that case there's always one orbit which is Zariski open. And then you say a Langlands parameter is open if the nilpotent element lives in the open orbit of this vector space of nilpotent elements. That's a very natural thing to define, but I think that before 3 years ago I had not seen it. But okay, this is very similar to what we did for Hecke algebras. And well, in fact, the condition is not very strong. In fact, almost all Langlands parameters are open in this sense. Like if you do it for GL2 with the things coming from the torus, then you're hard pressed to find something which is not open. In fact, there's only one possibility which is not open if you take the parameters, say q and 1, and then n to be the zero element, but all other things are basically all other things are open. So this open condition is, well, almost all Langlands parameters are open, but of course there are some which are not. And well, so for these open parameters, one can prove just by, well, Lie theory, root systems, and looking at semi-simple complex Lie algebras, you can prove that a Langlands parameter which is bounded in the traditional sense is always an open parameter. You can also prove that a Langlands parameter which is discrete in the traditional sense is always an open parameter. And that's just playing around with root systems and Lie algebras. It doesn't achieve much, but it tells you already something, namely that if you have in the local Langlands correspondence, well, yeah, you know bounded parameters are going to correspond to tempered representations. Discrete series representations will correspond to discrete Langlands parameters. And there, this already predicts that the standard module obtained from, well, yeah, a packet of square integrable representations is irreducible and has an open parameter. Well, that the standard module is irreducible is almost obvious. So that doesn't tell you much news, but it does tell you that in fact for discrete series representations or tempered representations, the Langlands parameters are supposedly open. So now let me say also translate the previous results about Hecke algebras to these P-Adic groups. If you have a P-Adic group, you assume that there is a local Langlands correspondence with some properties, then and you have a module, a standard module, say, coming from an open Langlands parameter, then in fact you can prove that this standard module is an irreducible module, so it equals its own Langlands quotient. And moreover, you can prove that whenever this standard module from an open Langlands parameter appears as a subquotient of another standard module, it can only appear as a sub-representation, not as a quotient or as a subquotient, only as a sub-representation. Well, okay, you may say, well, okay, big deal, it's a sub-representation, not a quotient. Well, this is my view as well, but it does affect, in fact relates to conjectures which people have proven. So this whole setup, which I done, can be made more precise if you restrict to, say, generic representations or quasi-split groups. Requires more work, but it can be made more precise. And in that case, it turns out for generic representations, you will always get open Langlands parameters or open Hecke algebra parameters. And then you can have these previous results that a module coming from an open parameter will only sit inside another standard module as a sub-representation, not as a quotient. And this is in fact which has been conjectured also by Kasselman and Shahidi as a, say, stronger version of their standard module conjecture, the so-called generalized inactivity conjecture. Also, I don't know, somewhere in the 90s they posted. So this is now proven with these methods. And this I can actually prove without going to the Langlands parameter side. This can be done entirely on the P-Adic side with Hecke algebras. So another reason why people have looked at this stuff more recently, well, say last 5-6 years, is related to Adams, Barber's, Vogel packets, which are in principle things which were defined for real reductive groups as some kind of geometric analog of Arthur packets for real reductive groups. This has also been defined for reductive P-Adic groups as an alternative to Arthur's definitions of Arthur packets for, say, classical P-Adic groups. And people have then tried to prove that these Adams, Barber, and Vogel packets are the same as Arthur packets. And, well, the definition of these ABV packets is in similar terms. You must also use the complex geometry of this vector space of nilpotent elements endowed with an action of a suitable reductive group. But then you must use further algebraic geometry, which is, well, further away than I ever got in algebraic geometry. So I don't understand very well what they do there. But at least if you look at what they wrote about it, it's always this Kazhdan-Lusztig conjecture is one of the first things they need to analyze anything about these ABV packets. So there it certainly plays an important role. And this is ongoing research. They have written a series of papers about it, but apparently the last word has not been said about this ABV packet. So I hope that my work on this Kazhdan-Lusztig conjecture will contribute somehow something to that. Okay, I think this was the last slide. Yes, it was. Well, slightly over time, apologies for that. But I thank you for your attention. And if you have any questions, they're welcome.